Well, hello friends. Welcome back to the show. Today we are going to do some relaxing profiling and optimization work. I figured we would take a look at the JavaScript test suite that we have. So currently, while I'm recording, it completes in 1.5 seconds. And that is pretty fast for test suite, but I figured why don't we profile this and see what we can find and see if we can't make it go a little faster. See, just by profiling it, we made it go faster. But let's take a look at what it's actually doing. So, if we flip this thing upside down, we can see that there's a lot of malloc and free going on. Okay. And then we have string unref, which is very suspicious, and a call to hash nonetheless. So let's see, what is this? We are creating a property table in JavaScript, and then the function that hashes a string or symbol for some reason is manipulating the ref count of a string. So that should be completely avoidable. And so we'll probably be able to get rid of at least this particular branch and actually probably all of these branches here. So that looks pretty promising. Maybe we'll start with that one. And then we have GC heap allocations when we are putting properties into objects and changing prototypes. Okay. And here we have more string ref count manipulation, again, when hashing string or symbol. So yeah, that one is definitely going to be our first target, the string or symbol helper. So let's see. And let's see if this thing shows up in malloc as well. It is here, string or symbol, although this is appending to the singly linked list. So our hash maps currently are built out of singly linked lists that hang off of hash buckets. So this one is not straightforward to fix, although I would like to switch to what is it called? Closed hashing at some point. But anyway, that one is a bit of a bigger issue. But we do have here string creation again into string or symbol. So string or symbol is definitely the place we're going to go look. So what is going on with this class? So string or symbol, by the way, is what we use as a key in object property tables in LibJS. Because an object, a property, can have either a name or a symbol as the key. So that's why we have this sort of helper class that wraps either a string or symbol, as you could guess from the name. And internally, it's just a void star. And then depending on the bottom bit, like the least significant bit in this pointer, we use that bit to determine if it's a symbol or a string. So you can see it right here. And of course, that's a very common trick since pointers are guaranteed to have the bottom 2 bits zeroed out normally. So you can put stuff in the bottom of pointers. If you need to smuggle some extra bits, you just have to take care to actually mask off those bits when you are dereferencing the pointer. Anyway, so I think, let's see, so I saw this thing right here. That's the create uninitialized. And string impl create. So that's when we're converting a property name. Let's see, property name to string or symbol. So this should not necessitate any kind of string copy, I think. Because if this property name is a string, then we can just use the existing string, because strings are immutable in Serenity. So here we are unnecessarily creating a string impl, which is the immutable inside of a string. So instead of doing that, we can just say string impl I think like that, and then we need to ref it. So that would be a static cast to string impl mputter. Oh, it's a const? Okay, all right. Ref. Yes. So that's fine. So in this case here, when we're just getting like a character array or a C string, then we have no choice but to construct a string impl. But if we are past a string always has or it doesn't always have, but a string is a wrapper around string impl, right? So we can just reuse the string impl of the string provided. Now, that string we're provided should never be a null string, so let's just assert that it's not null. Otherwise, this would make us very sad what we're doing here. Okay. So let's see, this should get rid of this path right here, this allocation. So I guess we can confirm that by just checking. Because then we have all the reference count manipulation when hashing. We have hashing in here. So we have traits for string or symbol, which implements hash. Then if key is a string, then key as string hash. Okay, so key as string returns a string by value. So this will construct a new string, which is a wrapper around string impl, and that string object will ref and unref the string impl. So that's where the hashing is coming from, I think. But let's just verify the malloc thing and then move on to the hash stuff. All right, so invert malloc. All right, we have string impl here, but the string or symbol is gone. So now we just have other ways of constructing string impls, but that's okay. Okay, great. So let me see. Let's just run the JavaScript test here on host to make sure that we're not doing something dumb, but it seems fine. Don't void unnecessary string copy in, or string impl copy in string or symbol from string. Yeah. Okay, and then here, if the key is a string, as string, So we probably want to have, I mean, we can't really return a const reference to a string, right? Because we don't have a string object here. We just have a void star. What we could do instead is we can just make a hash function, I guess. So here's what this thing does. Key hash, and then because then we are inside here and we have a bit more maneuverability. So we can do static cast const string impl. Hash? Yeah, we can just call hash on the string. Otherwise, if it's a symbol, what does as symbol do? It just returns the pointer with the bottom bit masked off. Right, so, and in this case we know that if it's not a string, we know that it's a symbol, so we don't even need to check that. And we can simply do that. So I think this should get rid of the ref count churning in hash, but we'll verify. U64. Oh, I wonder why this is working with 64. And why not U input or T? Because that seems suboptimal in a 32-bit build. Anyway. Okay, so unref is here, okay. But now we are in equals rather than in the hash itself. So what are these? Linked list. That's probably fine. String or symbol constructor. String or symbol constructed from a string or symbol is still heavy. Why is that? It's doing nothing but calling ref on the string impl. Okay, so that one is kind of unavoidable. So it's probably just the assertions here that are hitting us. We might benefit from always inlining this, but I think it's not the end of the world. It's not particularly heavy. Maybe it's a little bit heavy. What is it doing here? Let's take a look at the assembly. So the hottest piece is this, let's see, it's an exchange add and then a test. So I'm guessing that is manipulating the ref count. So xadd. Fetch add +1. Yeah. Wait, what are we testing here? We're asserting that the old ref count is greater than 0. Oh, and it's unsigned, so I guess that's why it's 0 flag check. Okay. That makes sense. Because with an unsigned type, only 0, in this case there's like only 0 and non-zero. There's no negative. So we only need to check the Z flag. So it's probably this assertion. And I don't particularly want to mess with that assertion. Anyway. So this is probably a good change. Avoid string impl ref count churn, hashing string or symbol. Yep. Actually, we can write a little bit more. Hash helper function, so we can compute the hash without having to construct a temporary string. Cool. Oh, actually, now I forgot about the equals. So that's the second phase of hash lookups. Of course, first, when you do a hash lookup in Serenity hash maps or hash tables, first we hash the thing you're looking for, and we search through all the buckets, and if we find something with the same hash, we also do an equality comparison. So it's the second phase. So this is just the first step of checking or doing a hash lookup. And then we'll also do equals checking on it. And since we're not specializing equals, so we'll just use the generic traits here, which simply does a equal equal, or an operator equal. So that would be this guy. And in the case it's two strings, then what we'll do is we'll do asstring. Okay, so that's going to produce yet more temporary string objects, which is going to be heavy. So let's see if we can fix that up. So if other is not string, then it's not a match. And otherwise, let's see. This impl is static cast const impl mputter. Other impl is the other guy's mputter. And then let's see. So if this impl length is not the same as other impl length, then it's not a match. So let's get that out of the way first. And then otherwise, we will simply do a memcomp. Other impl characters, this impl length. And we don't have memcomp, so let's just give ourselves memcomp. With this, I think we should no longer see equals generating more reference count calls. But we'll verify that, of course. I wonder if you're comparing two strings and you have a cached hash for both of them, like, is it worth comparing the hash before going into the character compare? Like, obviously, if you have to compare long strings against each other for equality, then if they both have a hash in cache, then you could use that to quickly reject mismatch strings at least. But I'm not sure about that. It's something to think about. Okay, 1.2, starting to scratch a little bit here at the surface of time. Ref count unref. So this is the clearing of the singly linked list. I guess that's probably during the construction of a property table, but this is the linked list stuff. I don't see any equals here. ToString or symbol is here, but that's probably okay. Or as a string, this will still produce a string. Or will it? Produces a fly string by const reference. So why would that churn the ref count? It should generate a ref, but not an unref. Maybe, oh, maybe it's an overload issue. Maybe we are this thing doesn't have a fly string overload, so it takes this constructor overload here, which invokes the implicit construction of a string from a fly string right here, which even goes out of line and does a ref footer copy. So we can probably avoid that, but one thing at a time. So let's see. JS, avoid creating a temporary string in string or symbol operator. Okay. And then we can simply give this guy an overload for fly string. And I think that will probably work out. We'll get rid of a little bit more ref counter. Just very systematic approach to this today, but I think it's nice to sort of iterate on a profile like that. So you make one little fix and then you see what comes up next, and you just keep going and shaving off things until you run out of things. Okay, so unref, no longer have any property name toString or symbol, so that's great. So what else are we looking at here? It's the constructor, but ignore him. Ensure property table in malloc and in free. So why are we here? There's somebody called property count. Wait. Why does property count call ensure property table? Oh, we compute the property count in an object by realizing the property table, like forcing it into existence. We can definitely avoid that. So let's see. Add string or symbol constructor that takes a fly string. This avoids ref count churn from implicit conversion in some places. Cool. All right, so to count the number of properties in an object shape, instead of reifying the property table, what we'll do is right here, we should probably call property count as well. So instead, what do we want to do? I guess we can just keep track of it. Okay. So, how do we keep track of this? Size t m property count. So whenever we add a property to an object, when you do something like o.f, something like that, then this is a put on this object, and that will turn into a put transition on the shape if we didn't already have an f property. And then when you keep going like this, we'll just put more properties into the shape, and every time we add a new property to the object shape, we need to bump up the property count. And let's see, so that would be when we create a put transition. That's when we construct a new shape. So let's see, allocate a new shape. This guy right here. So we're transitioning from the previous shape to a new shape, and the new shape will have property count is going to be previous shape and property count plus 1. Boom. Okay, I wonder if it's really that simple. Because we have, there are 3 types of transition in the engine at the moment. So, I mean, there's invalid, but there's put, configure, and prototype. And put is when you add a new property to an object that the object didn't have a property with that name before. And then configure is when you change the parameters of a property somehow. Like you can make it writable or enumerable or whatever, or change the state of those flags. That's a configure transition. So that one does not add a property. That did not work out quite well. Okay. And then prototype is when you change the prototype of an object. Anyway, let's see, meta. So this crashes, and then we catch sig abort, so we don't actually know what happened. It's kind of annoying. So let's just not catch that, or let's not, or yeah, let's just disable this code for now. Okay, so what does Valgrind tell us? That's in blah blah blah. Asserting in get own properties, property table ordered. Wait, did we do a lot of... Okay, so we're able to run many tests successfully. It's just that we eventually fail. So let's see what we can learn about that. Wait, what was the function? Property table ordered. So I changed this thing to call property count. I feel like that was not a mistake, but am I just thinking wrong here? Let me back up on that. Restore what was and see if that was meaningfully different, because if so, I have to think harder about why. No, it still crashes. Okay. Property count, and then we go out of bounds. We try to go out of bounds on this vector here. Why is that? Oh, wait. I know why. When we did the +1, we didn't look at the transition type. I was explaining it in the voiceover, but I was not taking care to actually look at it. So we should not bump the prototype at the property count unless it's a put transition. So that would be if transition type is transition type put. Otherwise, it's simply previous shape and property count. Still no good? Alright. Well, we're gonna find out why. Property table ordered, still failing. Oh, I guess if I construct a shape from a previous shape, I need to inherit the property count there as well. Okay, I was just being sloppy here. Previous shape, property count. So it has 3 constructors. Are we still crashing in the same place? Get on properties, property table ordered. All right, all right. Property table. So I guess here we can dump out the property count, debug, property count. Count old way, or yeah, let's do it the old way as well. So property table size. We'll see what the last thing that comes out is. 0, but if we do it the old way, it would come out as 2. That's interesting. So why is it like that? Shape. So if you construct a shape, there are these 3 constructors. Shape, shape, and shape. But this one has a property count of 0. And if we reify, I wonder why. Let's see, what test is this? Run test. I'm just going to dump out which test we are testing so that we can see what's going on. Test colon JSON parse reviver. That's the one that's failing. All right. What's going on in there? Huh? Let's just get a stack here instead. So where the heck are we? We are in reflect object own keys. Really? Own keys? Wait, who calls own keys? Own keys, okay. Reflect own keys. Oh, wait, it's part of the test suite. Own keys. Deep, so we're doing a deep object equals, and then we iterate the own keys of A and deep equal check against B. So that makes sense. And I'm guessing that to equal here is doing a deep check like that. But why? Why would we end up with... Wait, maybe there's another way to... Yeah, this is not the right way to go about this. Because if... we could have a shape that... if you do it like a delete, for example, the shape becomes unique because as long as you're only adding properties to an object, then the shape is only being like incrementally built up, right? But the moment you delete a property from a shape, then we sort of give up on trying to coalesce similar objects. And we just say like, okay, well, this is unique because delete is a fairly rare operation anyway. And once an object is unique, then it no longer has a shape transition chain to care about. It only has the property table. Property table becomes the canonical authority. And so that's probably why we were seeing the property count 0, because we made a unique object for some reason. So when do we set unique? Create unique clone. And this would happen when you call ensure shape is unique, which we call in a few cases. For example, when you have more than 100 properties on an object, we stop doing transitions. We just make it into a hash map, basically. And likewise, when you delete something, we also make the shape unique. And so yeah, so that's basically a way to disable shape sharing, and it will exclude this object or this shape from participating in certain optimizations, but it tends to be favorable compared to trying to maintain a sane reality in the face of disappearing properties. Anyway, so I'm guessing that this is going to be the issue, but let's verify. So what we do, we had that debug line here, right? So if they are different, property count is not property table, or actually, let's verify it this way. Unique is unique. So if this says that it is unique, then at least we know what the problem is. Unique, true. Okay, good. So property count is not reliable if we are using the property table directly. And do we do that somewhere? Property table. Oh, it's exposed, but it's const. Property table, blah, 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 blah. But when you do a delete, what happens? Delete property. Remove property from unique shape. Yeah, so here we go and remove it. But when you add something, add property to unique shape. Okay. So we can actually keep tracking it here. Property count goes up. And wait, so this thing will tell us if something was removed, right? Yes. Remove. Okay. I think that's probably an issue with debug line. Run file test. Well, why are you crashing now? Okay, that's taking too long. Property table ordered. Okay, maybe we're not as finished as I was hoping. Let's see. That property count looks too large. It looks like we did a -1 on a 0 right up in here. Now, why would we go and do such a thing? Clone. You make a unique clone, then oh, we need to actually populate the property count field when we make a unique clone. New shape. Property table size. Still suspicious. Still a very large number here. Oh wait, did I not? Wait. I have to do that after I assigned to the property table. Ah, there we go. Okay. So that was a little rough, but we made it through, and let's see. So this should get rid of. So the thing we wanted to fix originally was the fact that calling property count on a shape forcibly created a property table just so it could count the number of entries. Now, this should no longer be necessary because we'll track the number of entries in an integer. So let's see if we can verify that. Look at the times. Okay, so malloc is still called by ensure property table, but it only happens in lookup, not in property count. So that's really good. What do we have here? Ensure property table. I mean, yeah, we're building the property table from the shape transitions, so I don't know what to expect. I guess one thing is the fact that we are seeing free when we're building a property table, which tells me that we're not building it in the most efficient way, probably. We could pre-allocate space in the property table so that it will fit the ensure capacity for property count. So that's one thing we can do. I think because it shouldn't be necessary to free anything while you're building up a property table, because we should only be adding the exact number of properties that we have in our transition chain. But let's see if that actually gets rid of the free. Didn't crash. Free, ensure property table, it's still there. Why are we freeing here? I mean, actually it's just free called by ensure property table. So it could just as well be this vector here. Which we could totally put on the stack. In fact, I'm not sure why. I mean, it's not, we can't put it on the stack completely, but we could give him a little bit of inline capacity, because why not? Might get rid of malloc and free in some cases. or in any case where you have 64 or fewer properties in the transition chain. Let's try that. So yeah, so pre-size the property table and give some stack capacity to the vector here we make of the transition chain. We put that in a vector because of reasons, I guess, because we want to traverse it backwards. We want to traverse the transition chain from the root so that properties are added in incremental order. Because what happens is that when you do like this, right, then what happens here is that we start out with O being an empty object, and then when you add X, we do a transition to a shape that has the property X, and then when you add Y, we transition to a shape that has properties X and Y. When you add Z, we transition to a shape that has properties X, Y, and Z. So shape X, Y, Z. Let me write these out, actually. So what we're doing here is that we are walking, we are currently at this shape right here. And in order to create the property table, we have to walk backwards. Or not backwards, we have to walk forwards from here. And we don't have a pointer from here to here. So we do have a pointer from here to here. And we have a pointer from here to here. So that's what we do. We just flatten this linked list of shapes into a vector so that we can traverse it in this order. And now we're just giving a little bit of stack capacity to that vector. So let's see how that works out. I think that's probably where the malloc and free came from. But I may be wrong. Sure, properties table is still here. Free is, well, I don't see it, so that's positive. I mean, we still, if we have more than 64 properties, then we will malloc. And this will also malloc. So, actually, yeah, this will malloc, but there's no free anymore showing up in the profile, so that's good. Yeah. So first, let's do the property count thing. LibJS. Don't force property table reification on shape property count. Previously, whenever you would ask a shape how many properties it had, it would reify a property table. Reify the property table into a hash map and use hash map size to answer the question. This is often a huge waste of time. This can be. So if we don't need the property table for anything else, so this patch implements property count tracking in a separate integer member of shape. Okay. Pre-size hash map, the hash map, and vector used in shape ensure property table. Yeah. Okay. So wait, then what did we want to do? I forgot. We have unref here. Create, put transition, string or symbol. Wait, what is that doing? Create, put string or symbol property name. It's doing a copy construct. And then using the property name again here. Yeah, so that one is tough. Do we have some dumb crap going on somewhere maybe? Maybe in allocation. Allocate cell is pretty high up. Create put transition. Calls allocate, which calls allocate cell. So this is our main allocator function in the garbage collected heap. First it checks some flags. Checks if it's time for a periodic garbage collection. And then this here is definitely not very efficient. So here we look for a suitable heap block to allocate out of. And if something doesn't fit, but we just walk like the whole list of heap blocks in order. And this could probably get pretty chunky actually. Looking through, let's see. I am mixing up things here. Yeah, so it's looking through double digits at least heap blocks, and I don't know what's up with this error message. It's something new. I guess I can just use the old style. So let's see, we look through all of those blocks, compare until we find something where it fits, and then we call allocate on the block. Allocate will simply pop from the free list. This part is constant time, but the more heap blocks we have, the slower allocation will get, which is not unreasonable, but we could definitely be smarter. For example, we could put we could make lookup tables for the requested allocation size, for example. So instead of having to walk all of the blocks, we would just index into a lookup table with some quantized version of the cell size that we're looking for, and fetch a suitable block that way. And then we could even have two separate lists, like lists that are known to be full and lists that are known to have empty or free cells. At the same time, it's like it's not overwhelmingly many, so I don't know if it's the end of the world exactly here. This in particular feels like it could be in line though. Like, I don't know why this is out of line. Not that it was showing up, but we can definitely do this. We don't need you. Also, this is not entirely optimal because, like, we might end up putting a very small cell into a heap block with space for very large things. Like, we just choose the first fit. So it could in theory make the allocator more efficient by segmenting it better. Anyway, let's take a look at these again. Look at those times. Allocate cell, heap block constructor. What is it doing in allocate cell? Let's see. What's that compare here? So let's compare right here. It's probably the hottest instruction in that function. Yep. It's 60% of the runtime is spent in this comparison here, so it's definitely worth improving that, but I feel, unfortunately, I'm running out of time for today, so I'm gonna have to punt on that. But yeah, that'll be something to improve. Next, at least we were able to go down from 1.3 something to almost 1 second, which is a respectable progression for one evening of poking at this a little bit. So I think I'm gonna commit that one because I kind of like it, even though it's not the most important thing. Oops. Yes. LibJS, always inline heap block allocate. This thing is so simple and slightly and sits on the hot path, so just inline. Yeah. Okay. Good. Right, so I think this is going to be the end of today's video. So if you made it this far, then I thank you for watching and hanging out. It was a little bit different today than what we normally do, but I hope that it was interesting. Now speed is varied a bit, but these load times are very nice. Yeah, this type of work is fun to do sometimes, and I do feel like we could do a little bit more of it because we've been adding so many things lately and didn't really stop to work on performance for quite a while. So it's good to take a break and polish it up. Anyways, thank you for hanging out, and I will see you next time. Bye.